Hello viewers, welcome to today's lecture on transmission impairments and channel capacity. This is the fourth lecture in the lecture series on data communication. On completion of this lecture, the students will be able to specify the source of impairments as the signal passes through a channel, explain attenuation and unit of attenuation, the decibel, specify possible distortions of a signal as it passes through the medium, explain data rate limits and Nyquist bit rate because of the bandwidth limitation, and then distinguish between bit rate and baud rate, a new term we shall discuss. Then identify noise sources. Finally, we shall explain the Shannon capacity in a noisy channel, that is the maximum bandwidth, maximum information that can be passed through a noisy channel. The topics that I shall cover in this lecture are sources of impairment, attenuation and unit of attenuation, bandwidth of a medium, distortions, various kinds of distortions that can take place as the signal passes through a medium, data rate limits, Nyquist bit rate and baud rate, noise sources, and finally Shannon capacity in a noisy channel. As we know, to send data you have to convert it into a signal, either analog or digital. Then that signal has to be passed through a medium. It can be a simple medium or a complex communication system. Whatever it may be, the transmitter and receiver will be linked by some medium. And unfortunately, the medium that we use is not ideal. By that, what do we mean? Normally, by ideal we mean whatever is sent by the transmitter should be received by the receiver, but because of the limitation of the medium, that will not happen. There will be some impairments which we shall discuss. The impairments, imperfections of the medium cause impairments in the signal. What are the possible impairments? Number one is attenuation, distortion and noise. We shall discuss each of these impairments one after the other. First, let us consider attenuation. Attenuation can be considered as the loss of energy as the signal passes through a medium. We know from our basic knowledge of physics, as some signal passes through a medium, its intensity falls at the rate of d square, distance square. How we explain that? With the help of suitable unit. Normally, the unit that we use is known as decibel, dB. Here, dB is equal to 10 log 10 P2 by P1, where P2 is the power at the destination or point 2, and P1 is the power at the receiver, that is the at the transmitting end or point P1. That means power P2 is the received power in the destination, P1 is the transmitted power from the source. And so this ratio of P2 by P1 is taken as the relative measure of the loss of energy, and it is expressed as 10 log 10 P2 by P1. And this decides how far the signal can go without amplification. From our basic knowledge, we know that whenever the signal level is low, we can increase the signal level by amplification, by a technique known as amplification. And whenever we use the amplification, obviously the signal level can be raised. As shown in this diagram, for example, this is the point P1 from where the signal is passing, and it is going to point P2. And as you can see, this was the signal sent, and at point P2 it is very much attenuated. Now we use an amplifier between point 2 and point 3, and we get an amplified version of the signal. So an amplifier can be used to compensate the attenuation of the medium. And as I mentioned, decibel is a measure of the relative strengths of two signals, that means signal at the destination and signal at the transmitter. If P2 and P1 are signal strength at two different points, P2 and 2 and 1 respectively, then relative strength at the first point with respect to the second point in dB is, as I explained, dB is equal to 10 log 10 P2 by P1. So as you can see here P1 is the power, here P2 is the power, and here P3 is the power at this point. Now let me explain this with the help of an example. Let the energy strength or power at point 2 is 1/10 with respect to point 1. Then attenuation in dB is 10 log 10 1 by 10, that is minus 10 dB. It may be noted that the loss of power is represented by a negative sign. So we find that whenever there is attenuation, by looking at the sign of the that decibel value, we can find out how much attenuation, and also we can identify that it is attenuation. On the other hand, let the gain as it passes through an amplifier is 100 times at point 3 with respect to point 2. Then the gain in dB is 10 log 10 100 by 1, that is 20 dB. In this case, as we find, this is positive. So whenever we amplify, then we get a value which is positive. Whenever attenuation occurs, we get a value which is negative. Now as it passes through several points, say in other words a channel is in cascade with an amplifier, then maybe another channel, say from here there is another channel. So in this way it can be cascaded. So what we can do, we can add up the values, the dB values, to find out the final attenuation or gain at a point 3 with respect to 1. For example, in this case, say the signal strength at point 3 with respect to 1 can be obtained by adding the attenuation between P1 to P2, then amplification between 2 to 3. So which is equal to minus 10 plus 20 is equal to 10 dB. So here with respect to point 1, the amplification is 10 dB. So we find that finally from here to here, if we consider it is a gain, not attenuation, gain of 10 dB. So in this way the decibel values can be added whenever we have a number of devices or channel in cascade to find out the final value of attenuation or amplification, whatever it may be. Now as we know, we are interested in sending data through a medium, and we want to send it as fast as possible, or in other words, we want to send it at a high speed. Obviously we want the maximal possible speed, but at what speed we can send, that will depend on several parameters of the medium. What are the parameters of the medium? Let us see. First one is the bandwidth of the channel, number of levels used in the signal, noise level in the channel. So these three factors we shall consider one after the other to understand how fast data can be sent through a medium and or channel, and because of these parameters it is restricted. First of all, let us consider the term bandwidth. In the last lecture we have considered the bandwidth of a signal. What is the bandwidth of a signal? Bandwidth of a signal is the signal frequencies where most of the energy lies. Here it is somewhat different. Here by bandwidth refers to the range of frequencies that a medium can pass without a loss of 1/2 of the power, that is minus 3 dB contained in the signal. So you see the bandwidth term is used to refer to the bandwidth of a signal. It also refers to the bandwidth of a channel. So whenever we refer to the bandwidth of a signal, we refer to the major frequency components. On the other hand, whenever we refer to a medium, we mention that what is the range of frequencies that can be sent without much attenuation through the channel. For example, in this case, this is the amplitude, or we can say it can be considered, instead of amplitude we can write say amplitude, and that reflects essentially the attenuation or gain. So here we find that the attenuation is less in this part, and on both sides there is higher attenuation. That means amplitude is less, and half power is at frequency FL, and another half power is at frequency FH. So on both sides of this midpoint, there is the power level goes down to half, and so the bandwidth here for the channel can be considered as FH minus FL. That means F high minus FL. So this is how the bandwidth of a channel is represented. And as we know, the frequency components of a digital signal varies from 0 to almost infinity. However, at higher frequencies, the signal levels are gradually lower and lower. And as we know, a digital signal usually periodic in nature, not periodic in nature, and that requires a bandwidth from 0 to infinity. So it needs a low pass channel. Low pass means starting from 0 to F. So you require a channel which will not attenuate starting from 0 frequency, that means DC, to almost, so we can consider this is somewhat like infinity, a very high frequency, if we want to send all the frequency components of a digital signal. So bandwidth of a medium decides the quality of the signal at the other end. Some of the frequency component, if we restrict the bandwidth somewhere here, some of the frequency component will not reach. On the other hand, whenever we send analog signal, then we can send it through a band pass channel F1 to F2. So this is the frequency range of a band pass channel, and this band pass channel can be used to send an analog signal, because the analog signals have bandwidth like a has within certain range, say from lower frequency to upper frequency. Later on, when we shall discuss various modulation techniques, say amplitude, frequency and phase modulation, we shall see that these will generate signals having similar to a band. That means it can be passed through a band pass channel, and it has other consequences, as I mentioned in the last lecture. This will help us to send several signals through one channel. You can send, say, one signal between F1 and F2, another signal between F3 and F4, and so on. Several signals can be simultaneously sent, which we may call frequency division multiplexing, and we shall discuss about it in more detail later on. Now let us see distortion. Let us consider distortion. As you have seen, one important phenomenon that occurs is attenuation. Apart from attenuation, what occurs? Whenever attenuation occurs, we know all frequency components, it is assumed that all frequency components are attenuated uniformly. However, That does not happen in practice. It has been found that attenuation of all frequency components are not same. Some frequencies are passed without attenuation, some are weakened, and some are blocked, completely blocked. So we can see that there are three situations. Some are passed without attenuation, some are weakened, and some are blocked. This leads to what is known as distortion. That means what the transmitter is sending at the other end of the medium, the receiver is not getting the same thing. They are not same. So in such a situation, we can say that signal is distorted or it has suffered distortion. For example, this is a input signal, and this is the medium through which the signal is being sent. And as it is sent through the medium, at the other end of the output we get a output signal which is much different from the input signal, and this will be decided by the bandwidth of the channel or medium. Let me take an example and explain the effect of signal passing through a band limited channel. Suppose we are sending a digital signal 0100000100, which has bit rate of 2000 bits per second. Here the bit rate is 2000 bits per second, BPS. This is the 2000 bits per second signal we are sending. So this is the fundamental frequency of the digital signal. Obviously, apart from 2000 fundamental signal, it will have the various other harmonics like 3000 Hz, 4000 Hz, 5000 Hz, all the frequencies it will be present. However, they will be of lower and lower amplitude. Now, as we pass this signal through a transmission medium having bandwidth of exactly 200 Hz, we get a signal like this. So this is completely different from what was sent. It was a rectangular wave. What we are getting is a sine wave. That means only the fundamental is passing through the medium. The other frequency, higher frequency components are not passing. So here the bandwidth is 2000 Hz. That is the bandwidth of the medium. Now we increase it little bit, say to 3600 Hz. Then we find that signal is somewhat like this. That means another harmonic has passed through the medium. 3000 harmonic has passed through the medium. We increase the bandwidth to 5200. Some more harmonics have passed. We increase the bandwidth to say 6800 Hz. We find somewhat very close to the original signal, but definitely not same. Now we increase the bandwidth to 10,000 Hz. We find a signal which is very close to the original signal. And now when the bandwidth is 16,000 Hz, we get a very good quality signal, and we can see that means this will pass up to 8th harmonic, and as a consequence the signal is that we receive at the other end after passing through the medium will be very close to the original signal that we have sent. So with this diagram I have explained how a signal gets distorted as it passes through a band limited channel. Now apart from attenuation, I mean bandwidth limitation, there are other kinds of distortion the signal will suffer. One of them is known as attenuation distortion. Why attenuation distortion occurs? If the attenuation of the medium varies with frequency, this leads to attenuation distortion. Let us consider, let me explain with the help of a voice grade telephone line. Suppose let me draw a diagram for a voice grade telephone line. Here a voice grade telephone line has bandwidth from 0 to maybe 4000 Hz. This is your 2000 Hz, this is your 1000 and this is your 3000. And on this side we draw the attenuation, and this is 0, say this is minus 10 dB in decibel and this is plus 10 dB. And the bandwidth of the medium, that means the voice grade telephone line in this case, can be represented by like this. That means with respect to 100 kilohertz it is shown, at 100 kilohertz it is 0, so it will be somewhat like this. So we see that at 1000 hertz, it is with respect to 1000 hertz, attenuation is increasing at lower frequencies, attenuation is increasing at higher frequencies. So the higher frequency components will be attenuated more than the frequencies around this region. That means lower frequency component as well as higher frequency components will be attenuated more than this central part. What is the way out of this? How we can overcome this problem? This problem can be overcome with the help of a device known as equalizer. So we can put a equalizer to change the characteristic to somewhat like this. How? Say this is the transmitter and this is the medium through which the signal is sent. At the end of the medium we put a hardware known as equalizer, and then output of the equalizer is fed to a receiver. Now we see that medium and equalizer together is giving a bandwidth like this, and obviously in this case whenever the bandwidth is like this, then the distortion is much less compared to this one. That means this particular bandwidth we get only with equalizer. So we see in this particular case, whenever we use equalizer, the problem is less in case of digital signal. Problem is more in case of analog signal. Why? The reason for that is, for digital signal we have seen that the most of the energy is concentrated near the fundamental and lower harmonics. At higher harmonics, lesser and lesser energy is present. On the other hand, an analog signal can have frequency components over the entire range. So whenever it is attenuated at some frequency range, we get more distortion. On the other hand, in case of digital signal, problem is less severe. So that's why this kind of equalizer is used in case of voice grade telephone line to correct the bandwidth of the medium and to get a better signal at the receiving end. Now let us consider another type of distortion that occurs, that is known as delay distortion. And this delay distortion arises particularly in a guided medium, not in air. Later on we shall discuss about the different types of transmission media. We shall see that there are we shall be having two types of transmission media, guided and unguided. So whenever the signal is passed through a guided media like twisted pair cable, coaxial cable or optical fiber, it leads to delay distortion. What is delay distortion? Delay distortion arises because velocity of propagation varies with frequency. That means the signal components that we are sending will have different velocities for different frequency components as it passes through a guided media, and this leads to delay distortion. And again, let us take up the example of voice grade telephone line, and in this case we consider the delay. Earlier we considered the attenuation, here we considered the delay. On this side it is the delay, and delay is say varying from 0 to 4000 microsecond. And on this side, this is the frequency, that means the hertz. So 0 to 4000, that is the bandwidth of the medium. Now it has been found that in the middle part, the velocity is velocity delay is less. That means velocity is more. On either side of the frequency range, there is the delay is more or velocity is less. So what will happen? The lower frequency component will reach later, lower or upper frequency component will reach later than the middle frequency components. That means the frequency components in this range will reach earlier than the frequency component in this range and this range. So it may so happen that the lower and upper frequency components of the previous signal will fall on the middle frequency component of the present signal. This will lead to distortion. Again, this effect can be minimized with the help of using an equalizer, and the equalizer, after using an equalizer, the characteristic can be somewhat like this. So this is with equalizer. So with equalizer, the bandwidth is much better. That means delay distortion is much less, and bandwidth characteristic with respect to delay we find is much better. And in this particular case, digital signal is more affected. As we know, digital signal will be having many high frequency components. So we find that the delay distortion affects a digital signal more than an analog signal. This is opposite to that of attenuation distortion. Now let us consider the Nyquist bit rate. As we have mentioned, that the signal that we can send at the other end is dependent on the bandwidth of the channel, noise of the channel, and because of these parameters. Now let us see, in case of a noiseless channel, we assume that there is no noise, although it is not true in practice. But for an ideal channel, that means without noise, the maximum bit rate is given by the Nyquist bit rate, and it is explained, it is equal to C. That means Nyquist bit rate C is equal to 2 into B into log 2L, where C is known as the channel capacity, B is the bandwidth of the channel, and L is the number of signal levels. So we see here bandwidth we are taking into consideration, and number of signal levels. We shall explain this in detail later on. What do we really mean by number of signal levels? So it depends on the three parameters, rather two parameters in this case. The channel capacity depends on bandwidth and the number of signal levels that we are sending. Actually, to understand the number of signal levels, another parameter known as Baud rate has to be understood. Let us see what do we really mean by Baud rate. The Baud rate of a signal is, or the signaling rate is defined as the number of distinct symbols transmitted per second, irrespective of the form of encoding. We know whenever we are sending a digital signal, we know the bit rate and bit interval. Now, in a single bit interval, it is possible to send the number of distinct symbols that can be transmitted per second. Actually will depend on how much you are sending within the bit interval. If in a bit interval multiple levels can be sent, then we can send more information. For example, in case of baseband digital transmission, where the number of levels is 2, That means within a bit interval we can send either 0, we know that either 0 volt or 1 volt. So we have got two distinct values or two levels, 0 level and 1 level. So in this case it is 2. Now suppose it is possible to send 0 volt, 0.5 volt, 1 volt and then 2 volt, like that. Say let us take these 4 values we can send 0, 0.5, 1 and 2. So in this case number of levels is not 2 but 4. That means within a bit period, that means within that bit period we can send one of the 4 values 0 volt, 0.5 volt, 1 volt or 2 volt. In that case that L will be equal to 4. So depending on how many levels are present, the maximum baud rate will be dependent on that. So for digital transmission, as we know, it is equal to 1 by element width in second, that is equal to 2b, because here L is equal to 2. So this is the case for digital transmission with only 2 levels. The bit rate or information rate is actual equivalent number of bits transmitted per second. That means this allows us, whenever we are able to put more number of levels within a particular bit rate, a particular bit interval, then we can send more information for a given bandwidth. For example, the bit rate or information rate is the actual equivalent number of bits transmitted per second. That means I is equal to baud rate into bits per second. Baud rate means the number of possible values that we can send, and bit rate is actually the number of bits we are sending, bits per baud. So baud rate into n or baud rate into log 2m. So here m is the number of levels. So we find that for binary encoding the bit rate and the baud rate are same, because here the value of m is equal to 2. So log 2 is essentially m 1. So that means the information rate or bit rate is same as the baud rate. So information rate is same as the baud rate in case of digital and binary encoding or digital encoding. But for maximal use of the channel, we can use multi-level encoding. That will allow us to send more information to send through a communication medium. Let me consider an example of the telephone channel that we have already discussed, having bandwidth is equal to 4 kilohertz. Assuming that there is no noise, determine the channel capacity for the following encoding levels. Say we are considering encoding level 2 and encoding level 128. So when the encoding level 2, we get the channel capacity equal to 2b, that means 8 kilobits per second, or we can write it as kbps. On the other hand, when we are using 128 different levels for encoding, later on we shall discuss in details how multi-level encoding can be done. Then we can send 2 into 4000, that is the bandwidth, into log 2 128. That means it gives us 8000 into 7 or 56 kilobit per second, that means kbps, 56 kilobit per second. So you see, by suitable encoding, multi-level encoding through a channel having bandwidth of only 4 kilohertz, we can send a very high data rate, 56 kilobits per second. That is precisely what is done in case of modem. Modem can send 56 kilobits per second maximum, that is the maximum baud data rate. So we find that this is how we can send more information. So far we have neglected the effect of noise, but ideally that will not be so. A channel will always have some noise. So when there is noise present in a medium, the limitations of both bandwidth and noise must be taken into consideration. So far we have only taken into consideration the limitation due to bandwidth. Now let us take the limitation due to the noise. Why? A noise spike may cause a given level to be interpreted as a signal of greater level if it is in positive phase, or a smaller level if it is in negative phase. That means, suppose you are sending a voltage level 0.5 volt and there is a noise of plus 0.5 volt. That will make the signal level equal to 1 volt. Although 0.5 volt was sent, now we are receiving 1 volt at the receiving end, and so at the receiving end it will be interpreted as a signal of different level. So it will be, we shall get incorrect data. On the other hand, if it is negative phase, say plus 5, and the received signal, say noise is minus 5 volt, then together it will make it 0 volt. So we shall be getting another signal level, so which is also incorrect. So in this way, because of noise we may not get correct data. Particularly, noise becomes more problematic as the number of levels increases. So if we have only two levels, 0 and 1, which is represented by 0 volt and plus 5 volt, then problem is less. We can tolerate up to maybe plus minus 2 volt of noise. On the other hand, when we are using say 4 levels, we divide 5 volt into 4 equal parts, there it will be more susceptible to noise. Or if we increase, if the noise level, the number of levels is 128, then we can see that say 0 to 5 volt is divided into 128 different values, and if a small noise will change the transmitted noise level, and so at the receiving end we shall get a incorrect voltage level, signal level, and so it becomes more problematic as the number of levels increases. To quantify the noise level, a parameter known as signal to noise ratio use. Let P is the average signal power and N is the average noise power. Then signal to noise ratio is equal to average signal power by average noise power, P by N. Then signal to noise ratio in decibel is represented by 10 log S by N. So in decibel, this is the signal to noise ratio. Now for a given signal to noise ratio, the Shannon capacity for a noisy channel gives the highest data rate represented by C is equal to B, bandwidth is there, bandwidth part is there, and also it takes into consideration the signal to noise ratio. So the Shannon capacity gives the capacity is equal to B into log to 1 plus S by N, where S by N is the signal to noise ratio. So we find that in case of extremely noisy channel, C is equal to 0. That means log to 1 is equal to 0. That means whenever we try to send data through a very noisy channel, irrespective of its bandwidth, we may not get any, we may not be able to send any data because of this fact. That means if the signal, the noise level is very high compared to the signal level, then we cannot send any data through it. That means channel capacity is 0. Now we have two different parameters. One is Nyquist bit rate, which does not gives us a channel capacity based on bandwidth and number of levels that we use for encoding. Another is based on bandwidth and the signal to noise ratio. So we have to actually between the Nyquist bit rate and the Shannon limit, the result providing the smallest channel capacity is the one that establishes the limit. That means we may compute the Nyquist bit rate and Shannon capacity and find out which one is the lower, and the lower one has to be taken as the channel capacity. or the maximum information that can be sent through the medium. Let me take few examples here, particularly in case of noisy channel. So here the channel has got bandwidth of 4 kilohertz as earlier, and determine the channel capacity for each of the following signal to noise ratios: 20 dB, 30 dB and 40 dB. So we find 20 dB is essentially 100 signal to noise ratio. So it gives you a channel capacity of 26 point, Shannon capacity essentially is equal to 26.6 kilobits per second. For 30 dB, it is actually signal to noise ratio of 1000. It gives you a channel capacity of 39.8 kilobits per second. And for signal to noise ratio of 40 dB, we get a channel capacity of 53.1 kilobits per second. So you see, as the signal to noise ratio is higher and higher, we can achieve higher channel capacity. We get higher channel capacity for higher value of signal to noise ratio. Now let us consider a situation where we have got a channel with a bandwidth of 4 kilohertz, a signal to noise ratio of 30 dB. So we have to determine maximum information rate for 4 level encoding. So here the value of m is 4. So we are using 4 level encoding. So based on our Nyquist bit rate, we can calculate the value. For b is equal to 4 and 4 level encoding, we get 16 kilobits per second. That means 2 into b 8 into log 2 to 4. That means we get 2. So 2 into 4 into 2, we get 16 kilobits per second. On the other hand, if we take into consideration the signal to noise ratio of 30 dB, then we get Shannon capacity of 39.8 kilobits per second. So we find two values. One value is 39.8 kilobits per second. That is the maximum capacity that is possible. However, with full level of encoding, we can achieve only 16 kilobits per second. So smallest of the two values has to be taken as the information capacity. So in this particular case, when we are using b is equal to 4 kilohertz signal to noise ratio of 30 dB, then and using full level, that is based on these three values, full level encoding, the information capacity will be equal to 16 kilobits per second. So in this way, we can find out what is the information capacity in a particular situation. Let us take another example. Here a channel has bandwidth b is equal to 4 kilohertz, signal to noise ratio of 30 dB, and we would like to find out the maximum information rate for 128 level encoding. So here the Nyquist bit rate is based on Nyquist bit rate, b is equal to 4 and m is equal to 128 level, so we get 56 kilobits per second. On the other hand, because of the signal to noise ratio of 30 dB, we get Shannon capacity of 39.8. So here we see we are using a large number of levels, 128, which may provide us 56 kilobit per second, but because of the lower signal to noise ratio, the information capacity will be restricted to 39.8. So you won't get 56 kilobits per second, but we shall get 39.8 kilobits per second. So you see the smallest of the two here we have to take. So here it is limited by the signal to noise ratio. In the previous case, it was limited by the Nyquist bit rate. Now we can consider another example. Say the digital signal is to be designed to permit 160 kilobits per second. That means we have to send 160 kilobits per second for a bandwidth of 20 kilohertz, Determine the number of levels and signal to noise ratio. So here the problem is given in a little different way. Here the bandwidth is given. Bandwidth is given 20 kilohertz, and our desired data rate is given. You have to find out the number of levels and signal to noise ratio. So applying Nyquist bit rate to determine the number of levels, we get C is equal to 2b log 2m. So we get 16. That means 4 bits per baud. That means a single signal element has to represent 4 bits, so that the number of levels is 16. Applying Shannon capacity, we get signal to noise ratio based on this formula 4.07. So we see the with signal to noise ratio of 24.07 and number of levels equal to 16, we can achieve 160 kilobits per second data transmission through a channel having bandwidth of 20 kilohertz. So this example tells us how we can design a transmission system to provide suitable number of encoding levels and a suitable value of signal to noise ratio, so that we can achieve a desired data rate. I believe our discussion will not be complete if we don't discuss about the types of noise that is present in the medium. There are several types of noise that may corrupt a signal, and the most common noise types are discussed here. First one is thermal noise. What is thermal noise? Normally, if we look at a conductor, a copper wire, apparently we find everything, it is very calm and cool. There is no movement, nothing is taking place. However, if you look at the molecular level, we know each molecule is vibrating, and is vibrating within a range, and all the free electrons are moving around the conductor. So there is lot of movements, and this leads to noise because of the movement of the electrons, which are responsible for conducting current. We are getting some noise, and this is known as the thermal noise. And this thermal noise is dependent on 3 parameters, where K, the parameter K is the Boltzmann's constant, T is the temperature, absolute temperature in Kelvin, and B is the bandwidth of the channel. So we can see higher the bandwidth, higher is the noise. So N is equal to KTB. And another very important point that you must notice, this thermal noise increases with temperature. As the temperature increases, more and more noise increases. And that is the reason why you will observe that during summer, the quality of signal that we receive is poorer than in winter. Then the second type of noise is known as intermodulation. Intermodulation occurs when signals of different frequencies share the same medium. Suppose a medium is sharing a frequency f1, it is also sharing a frequency f2. Now, because these two signals are present, due to nonlinearities in the transmission system, it may generate signal like f1 plus f2. This signal f1 plus f2 will add, if it is in the same phase, if there is a signal of f1 plus f2 in the original signal. That means the noise generated because of intermodulation will be added to the signal if it is having a frequency component f1 plus f2. So we find that this intermodulation occurs when signals of different frequencies share the same medium. This is an example how a different frequency signal component is generated from two frequency components. Then the third type of noise that we commonly encounter is known as crosstalk. This crosstalk is due to unwanted coupling between two media. Whenever, for example, we later in the next class we shall discuss the various types of transmission media. There you will see, particularly in telephony and many other applications, a number of cables are bunched together and sent from one place to another. So whenever we are sending a number of cables side by side, the signal passing through one cable induces signal in other cable, and this leads to crosstalk. In our telephone network, the crosstalk is a daily phenomenon. We have seen that in telephone network we frequently encounter crosstalk. We hear some unwanted talk going on in the background. This is because of this unwanted coupling between two transmission media, that means cables. Finally, the impulse noise. This arises due to disturbances such as lightning and electrical sparks. This is not getting generated in the medium, but the environment is generating it. For example, in the rainy season there is lightning, or in an industrial environment there are electrical sparks, welding, turning on and turning off of switches. Various types of things can occur. That leads to radiation of electromagnetic signals, and that may corrupt the signal that is passing through the medium. And this affects more severely the digital signal, not the analog signal that much, because a 0 may become 1 or a 1 may become 0 if it is a digital signal. On the other hand, in case of analog signal, it will not affect much. Signal level will possibly change. If we are listening to voice, you will hear some disturbances, but that error is tolerable. But in digital domain, this error will lead to corruption of data. So with this we complete our discussion on the transmission impairments and channel capacity because of the limitations of the channel. Let us give some review questions which will be answered in the next lecture. Question number 1. Let the energy strength at point 2 is 1/58 with respect to point 1. Find out the attenuation in dB for point 1 with respect to point 2. Assuming there is no noise, determine channel capacity for the encoding level 4. Encoding level 4 and bandwidth is equal to 4 kilohertz. A channel capacity has bandwidth of 10 megahertz. Determine channel capacity for each of the signal to noise for okay, this need not be here. For the this part should not be for the signal to noise ratio of 60 dB. The fourth question is, the digital signal is to be designed to permit 56 kilobits per second for a bandwidth of 4 kilohertz. Determine the number of levels required and the signal to noise ratio. These are the 4 questions you have to answer, and answer will be given in the next lecture. And here is the answer of the previous lecture. Distinguish between data and signal. Data is essentially an entity which conveys some meaning. On the other hand, the signal is the representation of data in some electric, electromagnetic and optical form. So whenever data needs to be sent, it has to be converted to signal of some form for transmission over a suitable medium. Second question was, what are the 3 parameters that characterize a periodic signal? As we know, the 3 parameters are amplitude, frequency and phase. and amplitude is represented by A, frequency is represented by F, and phase is represented by phi. Third question was distinguish between time domain and frequency domain representation of a signal. Whenever a signal is represented as a function of time, it is called time domain representation. An electromagnetic signal can be either continuous or discrete. It is represented by ST. Whenever a signal is represented as a function of frequency, it is called frequency domain representation. It is expressed in terms of different frequency components and represented by SF. And the fourth question was what equipments are used to visualize electronic signals in time domain and frequency domain. For frequency time domain representation, we use cathode ray oscilloscope, and for frequency domain representation, we use spectrum analyzer. Finally, the last question was what is the round trip propagation time between Earth and a geostationary satellite. As we know, distance is 36,000 kilometers and speed of light is 3 into 10 to the power 8 meter per second. So from that we get a propagation time of 0.24 seconds. So we find the round trip propagation delay is about quarter of a second. It's a long time. Later on we shall discuss about it more. For the time being, thank you.